Hey there, my fellow intellectuals. How are you doing today? If you haven't seen my previous video on how I didn't pass the AP Physics exam in high school and I told that story, I highly recommend that you pause this video and watch that one because it'll help this one have more context. So without further ado, let's go right into reacting to the exam, the AP Physics exam that I didn't pass in high school. Okay guys, here we go. AP Physics C Mechanics 2013 free response questions. I legitimately have not seen this in about 7 years time, and if I'm going to be honest, I think I'm going to be a little bit sad reading some of these questions because obviously now in 2020 I'm a PhD candidate in physics. I have 2 degrees in physics, and looking at these questions now, it's probably going to be transparent as to what I should, how I should answer the questions. But obviously 2013, I was just a young high school student who was really into physics, but didn't really know much beyond what was on this exam, and probably knew less than what was on this exam because I didn't pass it. So we're going to get past that. We're going to try not remember the failure, but just look at it for old-time historical sake. Let's go on and try and see what this booklet has. So we have the College Board statement there. We have a table of conversion factors and constants. We have unit symbols. We have prefixes, values of trigonometric functions for common angles. Wow, I didn't remember this. 37 and 53 are common angles? That's kind of weird. 0, 30, 37, 45, 53, 60, 90. That's kind of weird. I don't remember ever learning about 37 or 53 when I learned trig, but okay. We have all these equations in mechanics and electricity and magnetism, which is starting to make me even sadder right now because I'm like, how did I have all this information and I didn't do that well in the exam? Again, trying to give younger Kyle some credit here. We have geometry and trig, we have some calculus, and okay, we have the questions. So let's go ahead and go right into it. So, time, 45 minutes, 3 questions. Wow, that didn't give us a lot of time here. So, answer all 3 questions. The suggested time is about 15 minutes for answering each of the questions, which are worth 15 points each. The parts within a question may not have equal weight. Show all your work in this booklet in the spaces provided after each part. It says a student places a 0.4 kilogram glider on an air track of negligible friction and holds it so that it touches an uncompressed ideal spring as shown in figure 1 above. The student then pushes the glider back to compress the spring by 0.25 meters as shown in figure 2. At time t equals 0, the student releases the glider and a motion sensor begins recording the velocity of the reflector at the front of the glider as a function of time. The data points are shown in the table below. At time t equals 0.79 seconds, the glider loses contact with the spring. And so what they have here is they have a table of velocities and times. So there is some, this motion sensor is recording the velocity of this glider at different times. And the first question is to plot the data points for velocity v as a function of time t for the glider and draw a smooth curve that best fits the data. Be sure to label an appropriate scale on the vertical axes. Okay, that's pretty easy. So you just take these points, plot them here, draw a best fit line through them. I don't think that gave me any problem if I'm trying to remember how I would think about things in 2013. Now it says the student wishes to use the data to plot position x as a function of time t for the glider. Describe a method the student could use to do this. Well, you know that position x is the integral of velocity v, and so the integral, right, so x is equal to the integral of v dt, and since this is discrete, right, these are all discrete points, it's not a continuous thing. What you could do is you could find the area underneath each section of the velocity curve, and that under each area you could figure out the position of the glider. And you also have to be mindful of, I think you'd have to be mindful of, is this thing going to rotate back? I don't think this thing is, so this thing has no negative velocities, as in if it just keeps going this way, if we define this to be the positive direction, and it's not going backwards, which I would assume to be the negative direction. So it looks like the position will always be, that makes sense, the position will always be bigger than 0. Okay, so for some reason I had in my mind that perhaps there would be like, you could make the glider go to negative positions if 0 was centered somewhere else. But okay, so that's good. So we'd have always the position being positive, and we have to sketch x as a function of time t. This may have given me some trouble because this is not a completely, like, I knew about integrals at this point, and I knew that position was the integral of velocity as a if you integrate it with time. But I think perhaps because it was discrete points, this may have given me some problems trying to draw it out. And I think just maybe I just couldn't do it in the time in a way that I think it says like label any intercepts, asymptotes, maximum or minimum with numerical values or algebraic expressions as appropriate. I think this probably just like freaked me out because I was like, wait a minute, all this stuff really? Because just looking, I can't visualize this plot, but I can't imagine it being too complicated and the integral of it being too complicated. So I'm not so sure. This may have given me a bit of trouble here. C, calculate the time at which the glider makes contact with the bumper at the far right. So you want us to calculate it. Okay, so you lose contact with the spring at 0.79 seconds. Oh, I guess what you could do, let's see. What you could do is like you could figure out, I guess could you figure out from the graph? So times 2 velocity. So one thing you could probably do is work out, if you know what the position is at that time, you could in theory, if you know when the glider loses contact with the spring and you know what its velocity there is, and you're assuming that it has no friction with the track, you could figure out the distance it has to travel based on where it is on this graph at 0.79 seconds, and then you can just use some kinematic equations to figure out how long it takes. Actually, you don't even really need to use the kinematic equations. Sorry, I think you could probably just use energy conservation. I'm trying to think here. How would I want to do it? Because you'd have the velocity at 0.79 seconds, and then the distance you'd have to travel, and then the velocity isn't increasing once it loses contact with the spring. So okay, so then it just becomes v equals d over t, and you solve for d, or you solve for t. Sorry, let's go with that. I hope that made sense. I'm not going to do out this exam because it's I'm not here to take the exam, but I'm sort of trying to work through the process of how I would do it now. Calculate the force constant of the spring. Okay, so we can look at some of these equations here, because we know the energy is what, half kx squared. That's the potential energy, sorry, it's half kx squared, and then the force is minus kx. So it's because I'm not actually writing this all down that I'm having a hard time visualizing how to do this, but that should be fairly easy to do. I'm skipping ahead, sorry, I'm going all over the place here, but that shouldn't be too hard. So with all that information, it seems to me that you would be able to work out what the k is fairly easily. The experiment is run again, but this time the glider is attached to the spring rather than simply being pushed against it. Determine the amplitude of the resulting periodic motion. So if it's just attached to the spring, then the amplitude should just be 0.25 meters, I think, if it's going to be in the same exact position as before. And then calculate the period of oscillation of the resulting periodic motion. So period, there's an equation for that. It's 2 pi, oh boy, 2 pi root m over k. Is that correct? 2 pi times root m over k. Yep, that's right. So that's the period of the spring. So we'd use that equation. So we have the spring constant from before, and then the mass of the spring was what, like 0.4? Yeah, then we put that in there, and we get the period. Okay, so first question down in my head here in 2020, as opposed to on paper in 2013. Only 2020 Kyle could make a wormhole and go back in time and feed myself the information that I knew. I know now as opposed to what I knew back then. Though I think that would be cheating, probably. Yeah, I don't think, but then again, there's no guidelines against you can't use wormholes on tests, right? Like, I haven't seen a test where it explicitly says don't give yourself the answers via time travel. So, it might work. So, problem 2, here we go. A box of mass m initially at rest is acted upon by a constant applied force of magnitude Fa. As shown in the figure above, the friction between the box and the horizontal surface can be assumed to be negligible, but the box is subject to a drag force of magnitude kV, where v is the speed of the box and k is a positive constant. Express all your answers in terms of the given quantities and fundamental constants as appropriate. A, the dot represents the box below. Draw and label the forces, not components, that act on the box. Okay, so we have Fa to the right. We have the normal force from the surface of, the surface here acting up. We have mg, just the weight acting down. And then we have the drag force in the opposite direction. I guess we could write that as minus bv if we define right to be positive and left to be negative. That should be all the forces. And there is no friction here, right? Yeah, the friction between the box and the horizontal surface can be assumed to be negligible. Okay, so that would be it. We'd have 4 forces. 1, 2, 3, 4. So good. B, right? But do not solve a differential equation. Wait a minute. Dang. They made us do differential equations on this exam. That could be used to determine the speed v of the box as a function of time t. If you need to draw anything other than what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figure in part A. Wow. Wow. They made us do differential equations. I mean, yeah, just write but not solve, but still. That's dang. I don't think we were taught like differential equations yet. I mean, obviously we work with differential equations in physics, even in mechanics, even if we don't know what a differential equation really is, or all the different kinds of solutions to differential equations and the difference between like ordinary versus partial differential equations. But I think this probably scared the daylights out of me when I saw it on the exam, because I was probably like, what? Differential equation? Possible. So what you could do, right? So now what I would do is that because the y directional forces, so the normal force and the weight are going to cancel each other out. So we're just going to have a competition between the applied force Fa and the drag force minus kV. And so you could use Newton's law, which is F equals ma. So you could have Fa minus kV is equal to ma. And then a is actually the derivative of velocity. So that's dv dt. And then there you go. You have your differential equation there. So again, not writing all this down, just saying it out into existence, just trying to show that I could take this exam now and do much better than I did back in 2013, even though that's probably a given. So determine the magnitude of the terminal velocity of the box. So the terminal velocity should be where the applied force and the drag force are going to be equal to each other. So that's usually the definition of terminal velocity, where the forces balance in the competing directions. And so I guess, let's see here. So we have Fa minus Kv is equal to, it's supposed to be 0. So that should be, can I do math right now? So it should be Fa is equal to Kv, so Fa divided by K should be the terminal speed, if I'm not mistaken. I think that's right. I think that's fairly right. Okay, part D. Use the differential equation from part B to derive the equation for the speed v of the box as a function of time t. Assume that v equals 0 at time t equals 0. Yeah, definitely probably did not do this question, because I don't think I learned about differential equations until at least my second year of college. I mean, obviously, like I said, in physics you do differential equations when you write down Newton's laws, but you don't solve them like using separation of variables or integrating constants or integrating factors or variation of parameters. You don't use any of those things in high school. At least I didn't use those in high school. So yeah, there's no way I answered this question at all, even though it would probably be fairly, simple now. I mean, because you have the differential equation there, and then I'm just trying to think. You probably have a log in there somewhere because you have a v and a dv dt on one side. You probably could use separation of variables, because I don't think Fa depends on velocity. So yeah, no, it would be fairly simple to do now. Now we have on the axis below, sketch a graph of the speed v of the box as a function of time t, and explicitly label any intercepts, asymptotes, maxima, or minima with numerical values or algebraic expressions as appropriate. Yeah, definitely did not do this because I didn't do this and maybe have not done that. So yeah, 2 is probably done terribly. Went terribly wrong for me on the actual exam. So, oh well. Finally, number 3. Oh boy, this is interesting. So we have this rope that like loops around this disc thing and attached to the ceiling. The disc of mass m equals 2 kilograms and radius r equals 0.10 meters is supported by a rope of negligible mass as shown above. The rope is attached to the ceiling at one end and passes under the disc. The other end of the rope is pulled upward with a force Fa. The rotational inertia of the disc around its center is mr squared divided by 2. A. Calculate the magnitude of the force Fa necessary to hold the disc at rest. Oh, interesting. Well, if you're applying this force FA on this side, there should be, I think, if I'm remembering, oh boy, I'm trying to remember here. I believe because the wall will provide that same amount of tension, right, on the other side. So I think it's probably half, the magnitude of the force FA is probably half the mass, or half the weight, half the weight of the disc. That's just my gut feeling, because I think there would be another FA right here. So you'd have two and if you have two FAs, you have the weight pulling downward, then you'd have 2FA equals minus mg equals 0, and then you could just solve for FA, which should be mg divided by 2. So that's what I think it would be. And that's probably as far as I can go in terms of calculating stuff in my head, because here we go. At time t equals 0, the force FA is increased to 12 newtons, causing the disc to accelerate upward. The rope does not slip on the disc as the disc rotates. Calculate the linear acceleration of the disc. Okay, so it says the rope does not slip on the disc as the disc rotates. That's important because that probably implies there's no friction there. So we could just assume that all the force is coming from the ropes. And so we would have essentially 2FA minus mg. If I'm right on the first part, it'd be 2 times FA minus mg equals m times acceleration. And then we know what FA is, it's 12, so we could just solve for that and do some algebra and solve it. So I know that was very general, but I think that's how you do it. Calculate the angular speed of the disk at t equals 3.0 seconds. Angular speed at t equals 3.0 seconds. Okay, so if the acceleration is a constant, then what you could do is, let's think here. I suppose what we could do is calculate what the linear velocity is at time equals 3 seconds. And then because we know what the radius is, angular speed is related to linear speed by v is equal to r times angular speed. So when angular speed is usually omega, so we'd be v equals r omega. We could probably calculate v at 3 seconds because we know, can we just assume it starts at 0 velocity at 0 seconds? Because then I think it would, then you could just work out via the kinematics what the velocity would be at 3 seconds, and then you could just multiply it by or just divide it by the radius of the disk, and then you can get the angular velocity there. Calculate the total increase in total mechanical energy of the disk from t equals 0 to t equals 3.0 seconds. I think what you would do for this one is that you would look at the change in kinetic and the change in potential energy. So the change in potential energy, we could just define the current or the initial position of the disk as a 0 point essentially, and then we can calculate how high it goes up in 3 seconds, and that would just be mgh, and so that would be the change in potential energy. And then for the change in kinetic energy, because this thing also goes up linearly, but it also is rotating, I believe, it will have a translational, as in just like a linear kinetic energy term, just something sort of moving in a line, but it will also have energy from the rotation itself. So those are going to be two different components of kinetic energy that we'll have to take into account. But yeah, that's how I would do that one. And then finally, the last question says the disk is replaced by a hoop with the same mass and radius. Indicate whether the linear acceleration of the hoop is greater than, less than, or the same as the linear acceleration of the disk. So a hoop is just like an open disk essentially. I think a hoop's rotational inertia is about, I think it's just mr squared, right? I think it's mr squared as opposed to mr squared divided by 2 for the disk. So if it's mr squared, the rotational inertia is greater, which means your rotational acceleration or your angular acceleration should be less than the angular acceleration of a disk. So the hoop would have a smaller angular acceleration, which means it should have a smaller linear acceleration then, because the radius is exactly the same. So we would say less than in this case. And there you go. That is the end of the exam. I wonder what I would get nowadays. Hopefully it would be a passing score at the very, very least, but I think I would do better than just passing, to be honest. So yeah, that was the exam. I hope you guys got to relive that experience with me, even though you didn't actually live it. I lived it, but I guess you guys watched me relive it. And that was kind of fun. That was kind of cool looking back at what I knew or didn't know back in 2013 in terms of physics. And it's pretty funny how, like, I thought this was sort of the end of the line for me when I didn't pass this exam, but was just terribly, terribly mistaken. And if only 2013 Kyle could see where 2020 Kyle has gone and done in physics, and he would not probably care too much that he got a 2 out of 5 on this exam. So yeah, that's the end of the exam, and I think that'll be a good stopping point for the video. So thank you guys for watching. As always, I always appreciate you guys taking the time to watch my videos. So as always, like, comment, and subscribe if you like the content, and click that notification bell so you stay up to date with all of my future stuff. And I hope to see you guys again in the future. So take it easy, everyone.